It's my pleasure to welcome Karthik Elamvazhuthi as a speaker today. He's a postdoc associate researcher at Los Alamos National Labs, and before that was a postdoc at UC Riverside and an assistant adjunct professor at UCLA. Karthik did his PhD from Arizona State University, and today he's going to talk about a transport theoretic view of nonlinear control. Karthik, the floor is yours.
Thank you, Aditya, for the introduction and also the invitation to present at the seminar. And also thanks to the organizers, Peter and Shuang. I'm going to be talking about. So my research is broadly on this general setting of control of probability distributions, and I'm going to be talking about this. How these set of ideas applies to. So there are some classical applications of these ideas, and then how we can use it even for classical nonlinear control. So to set the stage, let me just give you an instance of a control problem. Though many of you might be already familiar with it. So, for example, a standard model for a robot is the so-called unicycle model, where it has the system itself has 3 degrees of freedom, but it's under-actuated, and you have two control actions. The turning rate, which controls how much you can steer the system, and the actuation direction for forward and backward motion. So you have 2 degrees of actuation and 3 degrees of motion, and this is what makes fundamentally control problems interesting. Let me just start my. Sorry. Yeah, interesting. So the fundamental feedback control problem is to find these actuation signals as a function of state and maybe also time, so that the system is steered from some initial configuration to some target configuration. So this is the basic feedback control problem that we are interested in. Now, and also, please feel free to stop me and ask me any clarifying questions if anyone has. I'd prefer it to be interactive. Now, where we shift in perspective in solving these control problems is that instead of looking at how, so you have ordinary differential equation, and the classical way of solving control problems is to look at the system of ODEs and pose it as an optimization problem, or take a dynamical systems perspective. So here, what I am thinking about is, can we instead lift the system instead of looking at how individual states evolve? Can we instead look at how probability distributions propagate along this dynamical system? And can this give us some different kind of insight into how we should be controlling the system? And this kind of view is quite has received a lot of attention, for example, in the applied math and statistical physics literature, right? Instead of looking at how individual initial conditions evolve, you look at how ensembles evolve under the flow. Especially in theory of ergodic systems, this is a predominant view. So can we take a similar view for controls, right? Instead of controlling individual states, can we think about controlling individual ensembles? And from an application point of view, this has received a lot of attention. So my own background, my PhD was in control of robotic swarms. In that application, these probability distributions represented a multi-agent system, and the kind of predominant view in multi-agent control is that you have a graph and you have a finite number of agents. But in this setting of probability distributions, you model the swarm as a continuum or as a probability distribution, and hence this kind of justifies this approach of using the continuity equation and its other variants to control the swarm. So this has gained some traction in the multi-robot community, and more recently, this is also where so this is also has strong applications in generative modeling because one of the for example, if you're doing image generation, one way to pose the image generation problem is to transport your data distribution, which is modeled as a probability density. So you want to transport your noise density to some to some data distribution, right? And sample from images that way. And of course, probability distributions have also been good models of uncertainty, and hence this framework is also good for understanding how uncertainty propagates through a dynamical system and how can we control it. However, so this is some of the popular applications of this density-based perspective. What I'm actually interested in is not these applications, but the original control problem itself. That is classical control, right? Like, can this density perspective inform us something about the microscopic point-to-point control itself? And here I'm going to kind of touch on several different concepts that we often investigate when we look at a control system. And starting from controllability to how we can compute reachable sets. And I want to basically, advertise how this density perspective can give us insight about all of these and possibly give us new ways of doing computation and even analysis. So let's start with controllability. So just to jog our memory, what is controllability? I mean, so the question of controllability is if you have, say, for example, this unicycle model or your robot, can you go from some initial configuration to final configuration? And in the applications that I was talking about in robot swarms and things like that, the direction of this question of controllability goes in the following way. If your original state space system is controllable, is this in this density formulation, is your system also controllable? And turns out, at least intuitively, this feels like it should be the case, right? If you're able to manipulate the system from one point to another, then it turns out that you can find state and time-dependent feedback law such that the continuity equation can also be transported from any initial density to a final density. And this has been established in the linear setting, and I myself have worked in the nonlinear setting to basically for control systems which are of the control affine class, you can prove that it's controllable from any initial configuration to another. But what we are interested in is not in that direction, not where the microscopic controllability implies macroscopic controllability. We are interested in the opposite direction. So if somehow we knew the continuity equation was controllable, can we conclude that the other direction is also true? And this trivially has to be the case because the evolution of probability densities fundamentally captures something more general than the evolution of states, right? The evolution of states is a special case of the evolution of densities. But what we really want, what the real motivation behind this direction of the question is that the continuity equation is a linear equation. Even if your original, if you fix your control, it's a linear equation in the densities. Whereas your original control system, even if your original system might be nonlinear. So the hope is that can we somehow come up with a linear test of controllability for the continuity equation, and then use that to conclude something about your original nonlinear system? And can we come up with some kind of a computation test, right? And there are there's a rich body of work on controllability of nonlinear systems, but asking the question, there's a lesser amount of work on in this direction, whether we can use the continuity equation to understand controllability of your original system. So to facilitate my the next one of the fundamental results, I'm going to restrict the class of control systems to basically what are known as driftless systems, where you are allowed to actuate along all the associated vector fields that you have, and there's no underlying drift. So this negates, for example, the double integrator system, right, which can model force actuation on a particle with mass and inertia. But this is still a large class because it includes a lot of models that come from kinematic models that come from robotics. But as in general controllability, it turns out that we can say something useful for this class of models. So for the presentation, associated with this control system, I'm going to define a differential operator. So for each of these actuation directions Fi, which are the controlled vector fields, I'm going to define a differential operator, which essentially tells us what is the rate of change of if you have an observable along each of these flows, how does it infinitesimally change, right? So these are represented by these differential operators. And the idea is that using these differential operators, you can rewrite the continuity equation in the following way, where you use the adjoint of this differential operator to represent the evolution of the probability densities. So one interesting aspect of this differential operator is that you can associate with this differential operator, you can define the so-called sub-Laplacian. Now, for context, many of you might be familiar with Laplacians from different areas of applied mathematics and engineering. For instance, a Laplacian, whenever you have a graph, in order to understand the geometry of the graph, you associate a Laplacian operator with it. And you can understand a lot of the properties of how nodes are connected based on, say, the spectrum of the graph. And this is also well known in, for example, random walks in continuous spaces and say Brownian motion, right? Like properties of the Brownian motion. If you stay on some kind of a surface, the geometry of the surface is captured by the generator of the process, which is the Laplacian on that surface. So it turns out every driftless system can also be associated with a Laplacian, and we call it a sub-Laplacian because it's it's a degenerate operator in some sense. So in this setting, something very interesting was proved way back in 2009 that if the system is controllable, so this is again in the wrong direction that we are interested in, but it's still interesting, is that if the original system is controllable, then turns out the sub-Laplacian is invertible and the associated continuity equation is controllable on the set of positive densities. And what is even more surprising is that it's not just controllable on the set of positive densities, it's trajectory controllable. That is, it's not just that you can go from any initial density to any final density. Of course, the densities have to be positive. You can actually track any trajectory on the space of positive densities exactly. Now, this should be very shocking and surprising because you don't generically have this kind of property at the microscopic level. But somehow if positive densities kind of regularize the problem and you have trajectory controllability at the density level. However, so now what we are interested in from a classical control point of view is can we go in the opposite direction? Because what this is saying is that if the system is controllable, then the sub-Laplacian is invertible. So this is saying that if the underlying geometry of your space is, if the space is kind of well connected under the dynamics, then the sub-Laplacian is invertible. But what we want is the opposite. Can we go in the opposite direction? Can we conclude that if sub-Laplacian is invertible, then the system is controllable and hence connected? And turns out you can prove a version of this result. And this is something that I just did last year. So you can't get full controllability, but you can prove a weaker version of controllability if you know that the sub-Laplacian is invertible. So it turns out that if the sub-Laplacian is invertible, you might not be able to connect each and every arbitrary point, But you can say that you can control essentially like essentially all your points. That is, technically it means full sets of full Lebesgue measure to any neighborhood of your target point. And so it's kind of like an approximate controllability. So this is interesting because the sub-Laplacian operator is a linear second order differential operator. So if you have a test of invertibility for your sub-Laplacian operator, then you can conclude that your original control system is controllable in this approximate sense. And because it's a linear operator, we know many tests for invertibility of operators. And in fact, it's not just a linear operator, it's a self-adjoint linear operator. So you can use tests for positive semi-definiteness, which is essentially what a Poincare inequality is. So using this test for convex test for control for invertibility, you can conclude that the system is controllable. So this is one of the nice things about the density perspective. So what I showed was that basically this density perspective is useful for assessing controllability. But can we now go one step ahead? Because one of the goals of controllability is to answer the original feedback control problem, right? And a classical question is, does controllability imply stabilizability? That is, if you can control the system from any point to another using a time-dependent trajectory, can you come up with a feedback control law? Now, this is a notoriously hard problem, especially when your system is nonlinear. And for a large class of driftless system, turns out this can be, even if you know that the system is controllable, there are like hard topological obstructions to controllability. And this is famously due to Roger Brockett. There's a condition saying that you can't have continuously differentiable feedback stabilizers for a range of for most systems that are controllable. So, of course, a sufficient condition is if your linearizations of the system is controllable, but we have a large number of systems for which linearizations are not controllable. And an example is the unicycle model that I showed you initially, which has this obstruction and cannot be stabilized by continuously differentiable functions. But so one way people have gotten around this obstructions in different ways. One common way, for example, this is famously due to Jean-Michel Caron, is to use time-varying feedback laws. Another way to get around the obstruction is to use discontinuous feedback laws. But what I'm going to be talking about today is of using stochasticity to achieve stabilization. And how the sub-Laplacian operator that we looked at, which gave us a condition for controllability, also gives us a way to stabilize systems using stochastic perturbations acting through the system. So here now we have modified the system. We not just have a driftless control systems, but we are actuating, we are exciting through the control channels. We are exciting the control channels through Brownian motion. And then we are asking this question. I mean, okay, we can't solve the stabilizability problem for our original deterministic system, but can we solve the stabilizability problem in some stochastic or weak sense for this modified system? And because we are analyzing in terms of probability densities, we look at, instead of the continuity equation, we look at another variation of the continuity equation, which is the Fokker-Planck equation. And hence, you see this sub-Laplacian operator showing up because of the Brownian motion part of the problem. So turns out that when you look at the stochastic setting, there is a really easy way to solve the problem. So similar to in the fully actuated case, how you can, instead of gradient descent on a potential, you do a form of, you can have stochastic gradient descent. Similar to that, we can do a form of stochastic gradient descent along controlled directions. And turns out that if your system, if your sublaplacian is invertible and you use this control law where you take the sort of derivative only along the logarithm of the goal density, then using linear analysis of basically linear partial differential operators, you can prove that you can converge to this goal probability distribution. So this is really nice because you're getting like a closed form solution to any general, to a large class of general stabilization problem. And this is essentially answering the question that, okay, maybe controllability doesn't always imply stabilizability, but if we think about stabilizability in this weak sense of driving the system to target probability distributions, then the system is indeed controllable, and in fact controllable in some this exponential rate. So basically, these the lambda is negative, and m is some positive number. And so control theorists have now our own version of gradient descent, and what I refer to as non-holonomic gradient descent, the non-holonomy referring to the underactuation in the system. And this is also relevant in problems of, say, when you're, I mean, the so-called mean field control problems, where, so this is basically like a mean field controllability result, right? Like you can essentially, so if you want to control the system to a target probability distribution, you can use a state, just a purely state-dependent control law will drive you to the target configuration. And we can visualize this for the unicycle problem, right? As I said, this is a weak notion of controllability. It doesn't necessarily mean that you will always converge to the target configuration. But if you shape your probability density to be kind of localized around your target point,
sorry, we lost audio.
Back on the screen.
Not
stable.
Yeah, I think my. Can you speak something? I'm just checking if
Yeah.
you still have. Okay, all right.
Can you hear me?
Yeah.
Okay.
So we lost you for like 30 seconds there.
Oh, okay. Then I'll repeat what I was saying. So should I continue?
Yeah.
Okay, great. So for example, if you want to control this unicycle model to a target Gaussian distribution, if your actual goal is to converge to a target point, you can make your target objective to be a Gaussian, take the gradient along the logarithm of the Gaussian, and you kind of concentrate around the origin of the state space, and with higher probability as time t tends to infinity, you will kind of localize around that. And you can kind of visualize how the stochastic gradient descent looks for the system in position coordinates, right? So if you didn't have noise, this would just not be possible. If you use this control law, you would get stuck somewhere in configurations because basically the stochastic, I mean, the deterministic gradient descent for the system would be degenerate. And the noise kind of helps us get out of this degeneracy. So these are so essentially two things that I was trying to sell, that we can answer classical questions such as controllability and stabilizability. But what more can we do? And turns out that this perspective is also very useful in control synthesis of different kind, where, I mean, so the control that I just showed you could be a suboptimal control, and it gives you one control law which achieves stabilization. But does this perspective also give us insights on how to optimally control systems? And turns out the answer is yes. And yeah, so before I go, does anyone have any questions? Be happy to take any questions.
No, I don't think we have any questions right now. Thanks.
Okay.
I have a general question, but I don't know if it's time to ask. Back when you're looking at the positivity of the XX star,
right,
that's right. But we're looking at the positivity of the operator there.
Yeah.
Do yeah, that's right. With the sub-Laplacian.
Yeah.
Do any Lie algebra methods can they come into play here? The famous
Yeah.
full rank conditions. This also links up actually with the origins of the full rank Lie algebra condition.
Yeah. This is a great question because so this result by Lee and Keshin is in this direction because what it's saying is that if the classical Lie algebra conditions hold true, then the sublaplacian is invertible.
Right.
But this is going in the opposite direction and saying that, okay, if the sublaplacian is invertible, then the system is controllable in an approximate sense. But we don't know if this implies the Lie algebra condition holds true. So we don't know if the converse is true to the full extent, because that would then mean complete controllability. But I suspect that this is maybe true in some kind of weak sense. Maybe the Lie algebra condition holds true almost everywhere in the space. I don't know the answer to that, but I think it's all intimately connected, for sure.
Right. Knowing almost nothing about it, I was asking Stephen Yao about the role of the roots of the Lie algebra here, the root system. And he said, oh, it plays no role because the systems here don't have a root system. I just wonder if you'd speculate in that direction at all.
I'm not familiar with what a root system is. Could you?
I don't know. As I say, I barely know. I just began to read about I just began to read about root systems in the algebras. And so
Oh, okay. Yeah.
Stephen Yao, who'd done an extensive analysis of the Lie algebra condition for various systems and classification. And he said, oh, it plays no role here because our algebras are all, I think he said, I've got to be very careful here. I think he said they're solvable, I think. So I'm really, okay, I'll stop there because anything else I say will be most certainly wrong. But it was just a punt to find out if you explore.
Yeah, I mean, I don't know, but there is a lot of connection with Lie algebras itself and like the Lie brackets generated by the vector fields, but I'm not familiar with the things about root systems and stuff. But I should say that there's been a lot of parallel work in the partial differential equation community, right, on understanding these kind of operators using, the associated Lie algebras and Lie brackets and things like that. Similar, like in parallel to what the control community has been doing. So I think these.
Okay,
So
I'll ask my second question then. That this seems to be all set up to do all of these tests on manifolds by taking the Laplacian to a Laplace-Beltrami operator.
Right.
Have you explored that?
Yeah, it's the same. It's the same idea because the Laplace-Beltrami operator captures the geometry of the underlying space. So the Laplace Beltrami is usually associated with the Riemannian geometry of the space.
Right.
So when your system is under-actuated, you get a sub-Riemannian geometry, right? So this is, I mean, this is how Brockett, I think, kind of started the notion of singular Riemannian geometry was to basically, and then he like looked at these associator operators and stuff. So it's the same idea.
Right.
And just a generalization of that, I would say.
Right. Thank you very much.
Thank you. Thank you for the questions.
Can I ask some clarification question? So in the part where you introduced stochasticity, there is a circle with a dot for the. What does that mean?
So by that I was referring to because these equations can be in the Ito sense or the Statanovich sense. So I'm specifically looking at the Statanovich form of the equations.
I see.
Yeah. So you get these forward equations in a nicer form that I have a preference for the Statanovich equations.
Thank you. The other point that just the earlier point where you define these Fij's, I was wondering so you have the Fi and then you define it to be a sum of Fij's. I was wondering if there is a particular relationship between the notation you use Fij and Fi. Earlier, a bit earlier, where you.
Oh, did I use? Oh, sorry.
Yes,
Yeah, the
yes,
FIs
exactly.
and GIs are the same. Sorry, I mixed up notation. Yeah.
Um,
So the Fij's are the coordinate values of the vector field Fi. So it's the jth
okay,
coordinate.
I
Yeah,
see.
yeah. And the FIs
Okay,
are also the GIs that I later use.
I
Yeah,
see.
yeah,
Okay, thank you.
yeah. Thank you. Okay, so now that we have done that, we can go to optimal control. So another uh, aspect that this perspective gives us is, as I was saying, in control synthesis of different kinds. And specifically, for instance, one like we have this two different ways of dealing with control. Either we have methods for doing open loop control, or we have methods of doing like generating closed loop feedback laws, either using Lyapunov methods or say by solving the HJB equation, right? But so before I get to optimal control, just to motivate the method that I'm using, um, you, the, yeah, so a standard question that one can ask is, okay, if you know how to come up with a bunch of open loop control laws, that is, the control laws are purely time dependent, they're not functions of the state, can we use that to synthesize a closed loop control law? And there's no universal way to do this. And the problem is the following, right? Because the way you construct your control, your open loop control, it might be that the trajectories that it defines on the configuration space end up intersecting. And what is the meaning of intersections in the configuration space? It cannot be realized using a vector field. And what does that mean? So that means that it cannot be realized using a closed loop control laws unless it violates properties of uniqueness of solutions of your differential equation. So I'm not claiming that I will get around these issues of uniqueness, but there is a way to synthesize closed loop control laws using this perspective, which kind of seem to work in practice. Um, and and the approach is the following. So say you have some kind of a planner, which I denote by this function s, which for any given initial and final state gives me a trajectory and control pair. And this solves my control affine system. So a naive way to design a controller would be to say I have this planner and I sample from my set of initial and final conditions. So there's a typo, I just include the initial conditions. And I collect my control and trajectory pairs and I hope to learn a controller. So what is the problem? As I said, if you have intersections, there probably don't exist any controllers that can realize this, right? And so it turns out that people have developed some methods in machine learning, what they refer to as flow matching, to get around this. If you have two probability distributions, this problem arises in generative modeling and machine learning quite often. How do you connect them? How do you connect these two probability distributions using a vector field? We have the same problem. In our case, we have an initial some probability distribution, and we want to connect it to some point concentrated in space using a vector field which is constrained by our control design. So it turns out they have come up with a way, and this idea, what they have, which I'm not going to go in detail, but can be generalized to control systems. And the idea is the following. So turns out that if you have a bunch of random interpolations between your initial and final configurations, and you define this kind of stochastic control law, which I'm denoting here by this kernel function k, which is essentially a conditional. So instead of a deterministic feedback law, it's a stochastic law. It's saying that given x, I'm going to choose some control u. And I don't know yet what this kernel is, but because I have randomly interpolated trajectories, some such kernel exists. And turns out that using this continuity equation, you can prove that if you just take the mean of this kernel, you recover a deterministic feedback law. And this feedback law also has the same density level behavior as your original stochastic control. So you can mimic the behavior of your original stochastic interpolations using deterministic interpolations. And this is known as flow matching in the machine learning literature. And so this gives us a way to go from open loop synthesis to closed loop synthesis. So though folks in machine learning refer to this flow matching, this idea is actually very classical in controls. These kernels are nothing but what are known as Young measures, and goes back all the way to the work of Lawrence Young to prove existence of control laws in optimal control theory. But so far, it has mainly stayed in the theoretical realm in controls, and not. I mean, of course, people in stochastic controls use it as well a lot, but using it to actually come up with a computational control law, not so much. So. And you can see why we were hesitant, because this seems like we are taking a completely degenerate, irregular situation and try to make it non-degenerate by doing this averaging. Clearly, we are violating some laws of and the catch is that, okay, this the vector fields that you might get might still be irregular, right? Though you get a control law, it might be an irregular control law. But turns out that it still satisfies the continuity equation. So inspired by the success of our of people in machine learning, we can ask, oh, does this approach also work for control? And yeah, so then we can complete our pseudo algorithm where we just learn an averaging controller based on this conditional by taking the conditional expectation of the control with respect to with respect to the state. And yeah, and in theory this should work, right? And it works. I'll show you some examples. But the point I want to make is that this works not just for suboptimal control. We can use this idea to do general nonlinear optimal control. Now, so let's look at general nonlinear optimal control, right? Where the goal is not just to design some control trajectory to go from initial to final. You want to design an optimal trajectory. Sorry, there's a dt missing in my integral. So if we want to directly extend this idea, how would we extend this idea? We would extend this idea, the naive way to extend this idea would be that I can solve the open loop optimal control problem for each initial and goal configuration and then do my conditional averaging. But of course, this problem is hard to solve unless at the microscopic level, if you want to solve it. Because what you end up, the necessary conditions of optimality result in a 2-point boundary value problem. So you would, in order to sample from the initial and final states and the set of optimal trajectories, you would want to solve the problem for all initial and goal configurations, and then do your conditional averaging to recover your potentially optimal control law. Of course, the necessary condition doesn't always give you optimal trajectories. It can also give you suboptimal trajectories, but yeah, but what if we could solve it, right? So it turns out it's a hard problem to solve. So this is an obstacle from going from our open loop to closed loop synthesis to optimal feedback synthesis. So what do? So we take some inspiration from machine learning once again, and turns out that they have kind of found a solution to this problem of how to solve these decision problems of going from one initial probability distribution to another. So the classic way that people in machine learning used to solve this is in this forward direction. What would you do? You would start with some noise distribution, and you would learn a transformation that would take you to some final distribution of meaningful images, the set of all cats or landscapes or whatever your favorite is. So they realized recently in the diffusion modeling literature that maybe we should go in the opposite direction, right? Instead of trying to learn a transformation that takes you from noisy images to meaningful images, you should instead go from a set of meaningful images, add noise to it progressively, and then at the level of probability densities, try to reverse the process, and which is known as denoising. So when you're doing denoising, it's not that you're actually removing noise at the microscopic level. What it really means is that you at the level of probability densities, whatever is happening in the forward direction for the noising system, the denoising is exactly doing that in reverse. So can we bring this idea to control? And there has been some recent work in this direction. So I just met Ali today morning and said hi to him. But yeah, so him and some collaborators have done this work on basically mimicking this idea for control. So so instead of trying to go from initial states to goal states, we go in the reverse direction, right? You first add noise to the system, you propagate it to the set of all reachable sets, and then you do a kind of time reversal to go back to your goal states. And using the idea of time reversals from stochastic processes and SDEs, you can prove that for a large class of systems, this is possible. But of course, you don't need stochastic processes to do this. And we, in fact, going back to the Pontryagin maximum principle, we have our own way to propagate to reachable sets using the Hamiltonian system associated with Pontryagin maximum principle. And this is where we try to fix the problem of the 2-point boundary value problem using the idea of denoising diffusion models. So what we do is the following. So we remove the initial condition from the PMP system, and we think of the PMP system as if it's some kind of a noising mechanism. So instead of so what people do in diffusion models, where they stochastically excite your system using Brownian motion, we stochastically sample from the terminal condition of our adjoint equation, specifically the adjoint vector. And what that does is that it turns it from a 2-point boundary value problem to an initial value problem. And these are easy to solve. So now our algorithm is clear as to what we should do, right? So of course, this is a bad idea if you wanted to just solve the problem of going from one goal state to another, because you could just have a random lambda and it would not take you to your initial configuration. But the idea is that we don't use this for a single lambda, but instead we sample from a range of lambda. And what would that do? We know from geometric properties of the PMP system and associated like controllability properties of the system that if you sample from the adjoint state, it's going to have the following behavior. If you solve it reverse in time, when you propagate it backward in time, it's going to explode the whole reachable set. So this is a nice way for we start from the goal configuration, mimic this idea of denoising diffusions, and using this Young measures, we compute a conditional expectation, which is our deterministic feedback law. So we mimic this idea of going from open loop synthesis to closed loop synthesis, where we are now going from open loop optimal control to closed loop optimal control. And we don't have to solve a 2-point boundary value problem, just a huge family of initial value problems. And we recover a feedback controller in using sampling without solving an JB equation. So we can see now how stabilization looks. So our first process does noising, where you randomly propagate the system to reachable sets along geodesics of your system. And then you denoise the system by learning this averaging control law. So controlling a unicycle model, finding a stabilizing feedback control law is generally a hard problem, but turns out, so now you can frame this as a sampling problem and solving it this denoising based way. So this I think is a nice perspective on how we should be redoing we could be redoing optimal control using sampling. And there's a lot of machine learning involved in it, but I want to emphasize the control aspect of it because there's a lot of basically, classical ideas involved in this, basically Young measures and then continuity equation and things like that. But there are layers about this where you have to learn this, where this learning part has to be framed as a neural network learning problem and things and stuff. And I'm happy to answer questions if anyone has any questions about it. So I think I have like 5 minutes. So the next part, I'm just going to breeze.
Yes.
Yeah.
So because of the timeline, I ask my question later.
Yeah. Sure. I'll just breeze through the next part and then anyone can ask a question. So I just want to emphasize that using this idea, of course, you don't get globally optimal feedback laws, but you only get, but for LTI systems, you can prove that the control is optimal because the trajectories don't intersect and it's all a convex cost. And for nonlinear, you don't get that it's an optimal feedback law, but you at least get a feasible feedback law, which I think it's still a big win, right? Because we're using the Pontryagin maximum principle to give us a feasible feedback law. So traditionally, the PMP system is usually used to design open loop control laws. And to the next thing that I was going to talk about, which I'm going to rush through, is that you can also use this for computing reachable sets. So there are some ideas on using sampling for computing reachable sets by randomly sampling from the controls. But this has like a lot of problems because if your underlying system has an attractor, you kind of converge to an attractor and things like that. But if you use this transport formulation, you can do more uniform kind of sampling from your reachable set, basically by enforcing an entropy cost in your cost functional. But you can see that how basically you can again pose the reachability problem using this transport formulation. And essentially the idea is that you do analysis using your continuity equation, but you do computation using sample-based methods and the PMP system and things like that. So that concludes my talk. So I want to basically say that maybe this is a time for a more measure-theoretic approach for control, similar to the success of geometric control. And there are a lot of advantages of this perspective. And of course, a good if we want good computation methods, we need like good perspectives of both the density perspective as well as the microscopic perspective. These are some references which the talk was based on. And I'm also collecting some notes, trying to, consolidate these ideas. You can find them in my blog. And this is all from a bunch of collaborations that I've had over the years. So yeah, thank you. If anyone has any questions, I'd happily take them.